All right, so good evening, everyone. My name is Gioia Rau. I'm a program director at the National Science Foundation. I manage the portfolio of Stellar Astrophysics, among other things. And I also hold a research assistant professor position at Catholic University of America and a visiting researcher position at NASA Goddard Space Flight Center. And so today I want to bring you on a journey between stars and exoplanets. So let me get at the heart of this exploration right away. In this image, we see an artist's representation that is not to scale of how common planets are that orbit stars in the Milky Way. Sorry, and these exoplanets are planets that, as the word says, are outside our own solar system. And so they orbit stars outside our own sun. And also other stars that are in other parts of our galaxy, more likely also in other galaxies. And so our sun is the star in our own solar system, but in the universe there are, of course, many different type of stars. So let's see how and why. So what are the different type of stars? Stars are born from the gravitational collapse of cold, dense molecular cloud. And so this turbulence deep within this cloud create knots with enough mass that the gas and dust can begin to collapse under their own gravitational pull. And as the cloud collapses, it fragments into smaller regions, which in turn contract to form smaller stellar cores. And the material at the center begins to heat up. And so these are the protostars that spin faster and faster and heat up as they condense. And then a dense hot core forms and begins to gather dust and gas. And so not all of this material ends up being a part of the star. The remaining dust can become planets, asteroids, comets, or remain dust. And so these images that they show you here, it's taken by the iconic Hubble Space Telescope. It's called the Pillars of Creation, and it shows these clouds of interstellar gas and dust in the Eagle Nebula about 7,000 light years away, and it's home of this star formation. So what do I mean by evolved stars? What are the different type of stars? So in the 1700s, the chemist, biologist, and philosopher Antoine Lavoisier said, nothing is created, nothing is destroyed, everything is transformed. And well, this is also valid for our universe. In fact, stars born with a lower mass that are on the left side of this image, from 0.8 to 8 solar masses will evolve as red giants and will develop stellar winds. These winds have introduced most of the material into the interstellar medium, and this material is forming their atmosphere. They will become first a planetary nebula and then a white dwarf. On the other hand, if the initial mass on the newborn star is on the main sequence is greater than 8 solar masses, the star will evolve as a red giant, managing to burn increasingly heavier elements in its core until the fusion of silicon into iron, which is the tip point, so to say, and it's the beginning of the end, which leads to the star to explode as a supernova and eventually to form either a black hole or a neutron star. So in particular, I will tell you more today about the evolved stars, which are dying stars. These stars are red giants and red supergiants, red giants on the lower mass end and red supergiants on the high mass end. And these are the stars that are contributing. They're interesting because they are contributing the most to the chemical enrichment of the universe through their dust. And this in turn contributes to the formation of new stars and planets in a true cosmic recycle of matter. And in fact, one of the main open questions in astrophysics is still, how did we get here? How did life come on Earth, and what all of that imply? So we know that primordial nucleosynthesis in the universe formed hydrogen, helium, and a small amount of lithium. And so most of the atomic elements necessary for life on Earth were basically produced by nucleosynthesis inside stars. And it's especially during the late stages of stellar evolution that these heavier elements form molecules and condense into the dust grains, which then the stars, through their wind, expel into the interstellar medium. The expulsion of the material can be quiet, like in the case of red giants that pass through a very high mass loss phase that is called AGP, asymptotic giant branch star, or can be explosive, like in the case of red supergiants that turn into supernovae. And so you see here a table of elements in the context of stellar production. So as I mentioned, hydrogen, helium, and a small amount of lithium is formed in primordial nucleosynthesis, but then you see in the legend where other elements were formed, for example, dying low-mass stars, white dwarf supernovae, cosmic ray collision, margin neutron star, and so on. And in fact, most of the elements that make up our own human body were formed basically in these stars. In fact, think about this, the calcium in our bones, the iron in your blood, even the oxygen that you all are breathing right now were all produced in these dying stars. There is no other way on Earth to synthesize these chemical elements. They all came on Earth during the formation of our solar system. And you can see here that really truly the composition of the human body is made of this stardust. So it's true what Carl Sagan was saying, we are all made of stardust. And in particular, astronomers use this diagram called Sprung-Russell, from the name of the two astronomers who invented it, to classify stellar evolution. This diagram shows the temperature on the bottom that increases toward the left. This is for historical reasons. And the luminosity then increases normally from bottom to top. And we say that the star spends most of his life on its so-called main sequence, where our own sun indeed is still located. And in its core burns hydrogen into helium through nuclear fusion. In particular, our sun is a G-type star, but our sun, the sun, in 5 billion years will exhaust basically the supply of hydrogen through nuclear fusion processes in its core, and so the core will contract and its temperature will increase, causing an expansion and cooling of the outer layer of the star, and this is when the star will become a red giant. And there are predictions that the outer layer of the sun will arrive to engulf the Earth and even beyond. But the physics is very different in different type of stars. So let me give you an example of, for example, our sun in comparison to these giant, in terms of radius, evolved stars. The sun has a radius of only 700,000 kilometers, about 100 times the radius of Earth. And if you think it's great, well, just think that instead the radius of these red giant stars can reach up to 100 times that one of the sun. And so the central figure that I'm showing you here is not on scale, but on the bottom right side, you see a rectangle where actually those dimensions are on scale. But not only the dimensions are different, but also the physics of the different kind of stars are completely different. For example, the convective part in the sun extends from a depth of 200,000 kilometers up to the visible surface of the sun, while in red giant stars is much more bloated and includes more than 35 times more mass than the sun. So let's see how this mechanism of convection, that is basically one of the ways to transport energy, works. So I'm showing you here on the left side a composite video made of very many images taken from a Swedish solar observatory. While here on the right-hand side, you see the time is passing in years on the top right of the video. And those are simulations of these huge convective cells that are on the surface of the stars. So convection is on the surface of red giant stars. So left is sun and right is red giant stars. Convection is really important in stars in general. It's one of the way to transport matter and therefore thermal energy through convective motion. And basically through this motion, the energy is brought to the outer layer of the stars, so to the surface. And convective stellar motion consists of movement of the plasma basically inside the stars. But you can see how different is it, for example, in the sun, that you have these small granules in this image, in this video made of real images. And the image on the right, instead of these that are simulations, because as you can see, the time passes very fast, so it will be very difficult to have all these. There have been images taken actually with a technique that is called interferometry. I will talk to you shortly about, but not video yet. And so these images of simulation also because of this video simulation also because these stars have this extensive atmosphere that is really difficult to be able to see through. So how do we study these stars? So the best way is to observe them at different wavelength and ideally in a panchromatic way. So panchromatic is a word that comes from ancient Greek. It means, so panta means all and chroma means color. So ideally in all the colors, that translated to the world of physics means at all the wavelengths. So I produced this image here to show you how the panchromatic way is really a powerful way to study these stars by accessing the electromagnetic spectrum basically through these different windows that all the different telescopes provide us. It's like looking at a landscape and looking at it through different windows. Different windows show you different parts of this landscape, and so the combination of data obtained at different wavelengths will prove basically different part of the physics of these stars. And so here is a selection of the telescopes that I use in my research. And you can see that they cover a large part of the electromagnetic spectrum. And so what is the most important parameter? I'm sure not all of you know, for a telescope, the diameter of the mirror is what determines its power to collect photons, right? And so the larger the mirror, the more photons we can collect, and the more we can reach the smallest details of the objects we want to study in the cosmos. But how can we do this? So by increasing the size of the primary mirror of a telescope, we have a better resolution, but building mirrors larger than a few meters in diameter is very expensive, and it's a immense engineering challenge. The main problem to overcome is the weight of the mirror itself, which causes, under its own gravity, causes distortion. And so to overcome this, there are some remedies, such as the use of active optics under the mirror to control and compensate for deformation. And this has allowed the transition from telescopes with mirrors of about 4 meters in diameter to the current generation of optical telescopes that range from 8 to 10 meters, such as the one at the Very Large Telescope in Chile, the European Southern Observatory one. But using segmented mirrors with active optics, ESO's planned extremely large telescopes will have a mirror of 39 meters in diameter, and yeah, here in this picture is shown a comparison of all the mirrors with a human at the same time on scale. And so one of the most powerful technique for observing this star that doesn't involve building larger and larger telescopes, we have seen that we have a limitation. It's combining the light. It's a very smart way of basically combining light obtained from various telescopes together to create a virtual telescope that has the resolution of a telescope mirror up to basically the largest distance of these telescopes. And so it's a very powerful tool to study the universe. It's called interferometry. Here I show you the Very Large Telescope Interferometer in the Paranal Desert in Chile. There are these fixed 8.2 meter diameter telescopes that are the large one, and then you see the small, quote quote small 1.8 meters that the great part about those telescopes is that they can move along these tracks, and so in this way you can change their baseline. And the baseline is the most important parameter because it's basically the resulting power, the resulting resolving power is proportional to this distance or baseline between the telescopes themselves. And so to give you a concrete example, current interferometers such as CHARA in California in the US can resolve details as small as the angular size of a nickel seen from a distance of 10,000 miles, which is roughly the distance from Honolulu to Italy. And so an example of the use of this type of technique are these recent image of a study showing how a stellar spot on this star Epsilon Eridani was detected through interferometry. And it's the first interferometric detection of a stellar spot on a sun-like star. And this work is really important because it helps us distinguish the stellar activity that it's full of these spots that go around the sun to, for example, an exoplanets that pass in front of the star. Another example of the use of optical interferometry that I wanted to show you is in this video, which begins with a wide field view of the Milky Way, including the prominent constellation of the Scorpio, and then continues with a zoom into the heart of this constellation, where we find the red supergiant Antares. And so you can see how the video zoom into this star, and then the final view shows an image of the surface of Antares taken with the interferometer at ESO, the Very Large Telescope. And this is the best image ever of the surface and atmosphere of this star. And so you can see how difficult it is truly to look into the atmosphere of the stars. Another amazing result obtained at VLT that I'm very excited about is about the great dimming of Betelgeuse. I'm sure you have heard about it. The star was dimming, the luminosity was going down and down, and everybody thought that the red supergiant was becoming a supernova. But actually, in this paper that we published a couple of years ago with my team, we discovered that not only the red supergiant was fading, but also its apparent shape was changing, as you can see in this video. And so I've discovered that the great dimming of Betelgeuse resulted from a localized cooling of the photosphere, which triggered dust nucleation in a gas cloud ejected by the star months to years before. And here on the right, we see the observation of the infrared light being emitted by the dust surrounding Betelgeuse in December 2019. And the clouds of dust are in this red and orange color, are formed when the star sheds its material into space. And the central part, you see that there is a black part. It's masked, and there's a little hole that is actually what we see on the left. And this is circa 24 milliarc seconds in diameter. And so for now, we have only interferometers on Earth. But fortunately, or I mean, unfortunately or fortunately, depending on the point of view, the Earth atmospheres block us from observing many wavelengths, right? So the next step, the future, is really to build interferometers in space. And I'm leading the science side of several mission concepts in development. Those are space missions that we are developing at NASA in collaboration with other institutions and private companies. And today I cannot really enter into the details of all of these mission concepts, but I would love to tell you more about one of them that is called Artemis-enabled stellar imager. This mission concept this is a mission concept in development that was selected in the NIAC program by NASA. NIAC stands for NASA Innovative Advanced Concept, and passed the 4% rigorous selection of this program. And so I'm leading the science team, and I'm the deputy PI, and our goal is to build a 0.5 kilometer UV and optical interferometer on the lunar surface, and this will have a resolution 100 times better than the Hubble Space Telescope. So we have produced this video, and I want to show you here about the mission.
NASA's return to the moon opens up incredible opportunities for groundbreaking science. Imagine using extremely high-resolution imaging to study the surfaces and interiors of stars, probe the mysteries of black holes and active galactic nuclei, and study the dynamics of a wide variety of magnetic processes throughout the galaxy. This is not just a dream, it's within our reach. By starting with a 15-mirror interferometer, we can test and develop the necessary technologies. As we advance, we'll expand, lengthen the baselines, and increase the number of mirror elements, each upgrade seamlessly integrating into the existing system. With the Artemis program laying the groundwork for a lunar infrastructure, we have a unique chance to build a high-resolution UV optical imaging interferometer on the moon. A facility like this will revolutionize our understanding of the universe. Our study is determining the best design for such an interferometer, considering current and future technologies. We aim to push the boundaries of astrophysics, studying stellar magnetic activity, the nuclei of active galaxies, and dynamic processes on various scales. We'll explore the optimal size and configuration for the mirrors and develop a comprehensive plan for maintaining and evolving this facility with both human and robotic support. This lunar facility won't just advance UV optical interferometry, it will pave the way for other large space interferometers. Building a major facility on the moon will generate public and community interest, much like the collaboration between the Space Shuttle and the Hubble Space Telescope. It will inspire future generations, showing them that we can achieve great things together. Join us on this journey to the moon and beyond. Let's inspire the future and unveil the mysteries of the universe.
All right, so this is one of the mission concepts I'm working on, and I'm very excited. Let's see how. I hope I will tell you. I will manage to tell you more about it very soon. So, as we said, our sun will become a red giant in 5 billion years, and its atmosphere will expand so much that it will reach most likely the Earth's orbit. And according to our knowledge so far, we predicted that astronomers have predicted that what could happen basically are two scenarios. The first one, as it's shown in this video, the sun will basically engulf the Earth, which will then be enshrouded in the atmosphere of the by then red giant sun. And this video shows only this scenario. And the second, which I read in a science article a few years ago is that the Earth's orbit will be pushed by the very strong wind of the red giant sun. So, but how do planets of other suns work? And so, like planets of our outside our own solar system. In this image, it's a real image made by the ALMA interferometer, probably the most powerful radio facility. It's a radio interferometer facility in the world that the US is part of. And this is a series of protoplanetary disks. And so this basically, those are disks made of dust that form planets around young stars, and that have been observed by ALMA. And just the variety of morphology of this protoplanetary disk is incredible. And so how do these planets form? There is still a lot to understand about this, but the latest observations and theories suggest that planets, including those in our solar system, probably start out as a grain of dust smaller than the width of a human hair. And they emerge from the giant disk of gas and dust that surrounds young stars. And then gravity and other forces cause material within the disk to collide. And if the collision is efficient enough, the material fuses and grows grows more and more. And over time, the dust particles combine to form a bigger conglomerate of dust, which then evolve into rocks, and then evolve into bigger and bigger rocks up to a few kilometers across. And as these planetesimal orbit their star, they acquire material from their path, leaving trails of space empty, except for fine dust. And at the same time, the star gobble up nearby gas and pushes distant material even farther out. And after billions of years, the disk will have completely transformed, and much of it now, in the form of new planets. And so this animation shows how the material around the young star is shaped into planets over billions of years, and how over time these developing planets consume much of the disk's gas and dust. And so over the past 3 decades now, a large number of both terrestrials and space investigations are focused on searching for planets outside our own solar system. And NASA has a number of observatories that enable the science of exoplanets. There is Spitzer, TESS, Hubble, James Webb Space Telescope, and there was Kepler. And collectively, these telescopes are helping us on our journey to search for planets like ours. Indeed, about 30 years ago, 3 small planets were discovered orbiting a pair of rapidly rotating neutron stars known as pulsar. Imagine, we knew there were theory that there were planets around other stars that were not the sun, but we never observed them. So that was only 30 years ago. And so this was a landmark find and the first confirmation that actually planets exist beyond our own solar system. And so this discovery sparked a revolution in planetary science. Another big milestone in exoplanet science came in 1995 with the discovery of 51 Pegasi b, the first planet known to orbit a sun-like star. And this planet is about the size of a Jupiter and orbits stars in about 4 days. And imagine that Mercury takes 88 days, just as a comparison. And so this start a new class of object that astronomers now call hot Jupiters. And it was kind of unexpected. And so 51 Pegasi helped launch a whole new field of exploration. The pace of discovery really skyrocketed after the launch of NASA's Kepler Space Telescope in March 2009. Kepler was designed to determine the frequency of planets, and this box shows you the portion of the sky that was served during Kepler's 4 years of prime mission. Kepler detected exoplanets by noting basically the tiny brightnet dips that orbiting planet cause when they pass in front of the star, and this technique is called transit. In fact, there are several techniques to discover exoplanets: radial velocity, transit, direct imaging, gravitational microlensing, and astrometry. Sorry. So Kepler and other missions use this transit method, in which the brightness of the star is monitored, and the dips in brightness are detected as planets close in front of the star. And the amount of the dimming tells us that it's correlated with the size of the exoplanet, and the time it takes to complete an orbit, it tells us how far it is from the star. So in this way, we can measure periods very precisely, but sizes are only as good as the constraints that we have on the star itself. That's why it's very important also to study exoplanets hosting stars. So here are the locations of the planets on Kepler's detector from just the first few years of collecting data. Basically, Kepler taught us that planets are everywhere, and we now believe that planets actually outnumber stars in galaxies, in our galaxy, but also other galaxies. So Kepler also found a wide diversity of planetary architectures. Here are the multiplanetary system found from the first few years of Kepler data. And the orbits relative to the solar systems are to scales, but the size of the planets are not. And to date, we know that actually this figure is from the bottom part is from 2 years ago. So I'm sure that now it's way much larger. So far we know that there are more than 5,000 confirmed planets, and many other planet candidates that await confirmation. So many scientists were inspired to get into science because of sci-fi, and now we have many discoveries that actually, on the contrary, are inspiring sci-fi writers. Many exoplanets seem far stranger than the one science fiction writers have imagined. For example, these exoplanets, that was the first Earth-sized planet with a confirmed rocky composition, like the one of Earth, is known as Kepler 78b, and orbits its star very closely every 8.5 hours, making it, of course, too hot to support life. We have found over a dozen of planets that orbit 2 stars, and there are also 4 star systems. For example, Kepler 64b or PH1, a planet discovered by volunteers from the Planet Hunter Citizen Science Project at NASA. It's a bit larger than Neptune, and it's thought to be a gas giant, orbiting its host star every 137 days. Kepler also pushed the limits and found Kepler 37, which has 3 planets. The smallest is almost the size of our moon. K186 is a M stars, also known as a M dwarf or red dwarf. And those are stars that are smaller, cooler, and therefore dimmer than our own sun. And they range in size between 10 and 50% of the sun radius. And Kepler 186 is on the larger side. This is about half size and half the mass of our sun. And so here I'm showing you a schematic view of this complex system compared to the solar system, where the habitable zone of each system is shaded in green. So the definition of the habitable zone is basically the distance from a star at which liquid water could exist on the surface of the orbiting planet. And therefore, by definition, it's the area where the condition might be right, so neither too hot nor too cold, for life to exist. And so you can see here that the entire K186 system fits just inside the orbit of Mercury, of our, if translated to our own solar system. And so now we think that planets outnumber the stars in the galaxies, and that most stars may have planets. And just think about this, in our galaxy alone, there could be tens of billions of Earth-sized planets. And most of the planets discovered by Kepler are really far away, hundreds of light years away. But now that we know that planets are common, we can look at nearby planets that we can study with telescope from Earth, for example, as well, to look for atmosphere and maybe even signs of life on other planets. So Kepler's successor, so to say, was called TESS, is called TESS. Most of the planets discovered by Kepler are really far away, hundreds of light years, and TESS instead focused on nearby exoplanets. And TESS stands for Transiting Exoplanet Survey Satellites, and its primary goal is to search for small planets orbiting nearby and bright stars. Basically, to search for these planets that then can be used to do follow-up observations. And so the boxes on the left show the approximate field of view of TESS compared to Kepler, where each square is one camera of TESS, and TESS has 4 cameras, and it tiled over 85% of the sky. So these 4 cameras have stared at portion of the sky for weeks at a time, looking at millions of stars to search for these periodic dips in brightness that I showed you earlier, that could indicate that a planet is crossing in front of the star. Each camera consists of a CCD detector and a lens assembly and a lens hood. And you can see here the way that that TESS is scanning the sky. It was launched in 2018, and you can see that the real difference is that it observed the whole sky instead of staring only at a portion of the sky like Kepler. And so now we have really, really very many billions of light curves detected by TESS. And I'm telling you shortly how we are going to analyze them. Let me show you first a few observations that TESS made. This is a trio of planets around GJ 357, which is a red dwarf star 31 light years away, so quite close. The system Fortus planet with 6 times Earth mass is especially intriguing. It orbits in the outer part of the star's habitable zone, which is here in blue. And if this planet has an atmosphere thick enough to keep its surface warm, liquid water would exist there. TESS also found a planetary quadrupole orbiting the star L9859, a red dwarf 35 light years away. And this image shows a comparison of this system with a part of our solar system, Venus, Mercury, and Earth. And it highlights the similarity between the two. But the innermost planet in this system is the smallest. And up to the 30% of the mass of the third planet could be water, and the existence of the fourth planet has to be confirmed. But we do not know yet its mass and radius. That's why the possible size is indicated in dashed lines. There are also clues of a potential fifth planet that is the farthest from the star, but it's still unconfirmed. And if confirmed, it could be located exactly in the habitable zone of the sister. So I mentioned to you, how do we analyze all these billions of light curves that TESS observed. So those are just some of the discoveries TESS had made. There are so many unexplored data, and in fact, you observed so much of the sky and produced such a huge amount of data that analyzing them manually would be almost infeasible, not feasible. And so with my team, we built an artificial intelligence models, in particular machine learning ones, to explore this vast treasure trove of data in the most efficient possible way. And so this approach minimizes the human research effort required. And spoiler alert, we detected 181 new planet candidates. And I call them candidates because then they will need to be, in order to be confirmed, they will need to be observed also by another form, for example, radial velocity. And so we applied the use of these machine learning techniques to search for candidate planets, looking for these transiting exoplanets in nearly 67 million full-frame image light curves that TESS took every 30 minutes. And the strength of our method is that not only evaluates whether or not the dips in the light curves can be transits, but also identifies a priori light curves that could contain transits. And so we have created this convolutional neural network, which we have trained to identify basically planetary transit signals and discard false positives. So for those of you who aren't familiar with machine learning, as the name implies, basically the machine, the computer, needs to be trained to learn what to look for. And as the training data sets, we use 326 planets confirmed by the TESS exoplanets follow-up observing program. And so now, since a few years now, we also have another amazing machine, amazing telescope that, can tell us more about these exoplanets. Indeed, TESS was sort of our searcher to understand where to point GWST, but now we need to study the atmosphere of these exoplanets to really understand their chemical composition. And so GWST is able not only to identify planets, but also to measure what is contained in their atmosphere. It does so through a technique called spectroscopy, or the measurement of the intensity of light at different wavelengths. And so we could study the molecular content of the atmosphere of these planets, and this will be essential for the, to understand if they can or have been able to host life. So how do we do that? For planets passing directly in front of the star, well, we'll look for chemical footprints, identifying atmospheric gases such as water vapor, carbon dioxide, and methane, that absorb specific wavelengths of light from the star. And this is the spectrum of what we would see if we were to observe the planetary transit. So to let you understand the revolution that Webb brings, I show you this in blue is the part that we were able to observe with Hubble, and this is the part that we are able to observe with Webb. There are so many species that we are able to see. Here I show you only from 1 to 5 microns, but Webb actually is able to observe down to 10 microns with MIDI. And so carbon dioxide, methane, and many different molecules in these atmospheres. Webb will also study a protoplanetary disk formed and where planets form to reveal how the chemical makeup of the younger and old disk changes over time. And JWST has actually, started since a while. I mean, there is so much research already, but I show you here an early one of the early data collected, which shows the most detailed infrared exoplanet transmission spectrum made by a single observation using NIRIS, the Near Infrared Imager and Slitless Spectrograph instrument. And this spectrum reveals the atmospheric characteristics of the hot gas giant exoplanet WASP 96b. All right, and let me tell you more also about, we know that tests gave us a lot of places where to look at, and now we have JWST to understand the composition of the atmosphere. But in the future, the next NASA's flagship mission, which is the big mission like Hubble Space Telescope, James Webb Space Telescope, there will be Roman space telescopes who will also collect many data about exoplanets. And then after that, we will have the Habitable Worlds Observatory, which is a large infrared optical ultraviolet space telescope, which will be recommended by the National Academy Astro 2020. And HWO will be the first telescope designed specifically to search for signs of life on planets orbiting other stars. So it's a proposed NASA mission aimed at identifying basically Earth-like potentially habitable planets using orbiting bright stars like our sun, and it will, as a large ultraviolet optical and infrared space telescopes, it will be the first one to use a chronograph directly to study these planets for the sign of life. Here is a simulation of what we will be able to see with HWO, and the mirror is large enough to observe at least 25 potentially habitable worlds, and the HWO will be basically a super Hubble, surpassing the capabilities of HST. And so the mission is designed not only to search for life, but to understand more about the universe in general, and basically builds on the advancements of Hubble, Webb, and Roman. Okay, so that was my last slide, and I'm happy to take any questions you have.
I have a question about abundances of elements in these different types of stars. The sun has certain composition in its photosphere and in the corona. What about red giants and stars that have large star spots and that? How does the composition, is it the same or does it vary?
I'm not sure I understand your question. Like, your question is how different stars contribute differently to the enrichment of the interstellar medium?
Well, yeah, like if you look at the sun's corona, you can determine how much oxygen and carbon and nitrogen and iron and neon there is compared to hydrogen with certain values. And if you go into the photosphere, it's slightly different. But there's a solar composition. If you go to a red giant or stars that have large star spots, do you know how that composition would vary, would be different? Like the amount of...
yeah, I mean, definitely the corona of the stars, of the sun, it's very different than the atmosphere in general of this of red giants. So the atmosphere of red giants and then the phase actually producing most of these elements is called AGB, the asymptotic giant branch phase. Is the phase where the mass loss can reach 10 to the minus 5, 10 to the minus 7, 10 to the minus 5 solar masses a year, which is about 25 times month a year. And I mean, the atmosphere is so large that it's so extended that, I mean, we've seen it before. Basically, the star first forms these molecules of gas, and then the radiation pressure acting upon dust grain will form dust, and then trigger the wind into solar medium.
Anything else, George?
Well, I know that when you're going to start looking for the composition of planets, that we're using the Webb, then you've got to do all these molecules. And I wonder just how well the spectrum is for all these molecules. I know it's taken us a long time to understand the solar spectrum completely, and the X-rays and the ultraviolet. When you go into the molecules, you have all these various types of transitions that you can have and various different molecules. And so there must be a lot of research on molecular atomic physics. And if you're going to really figure out what the composition of these stars are. I think Sky and Telescope had an article on how the fact that it's rather difficult, I think, to do recently.
So, through interferometry is a very interesting technique because it can give you not only visibility, which is the main product that you obtain from interferometry to measure the size, basically, of stars, but also spectra.
Yeah.
And you can observe which molecules are in the stars. So, for example, I've studied a lot carbon-rich AGB stars. There is a lot of amorphous carbon and silicon carbide, around 12 micron. Oxygen-rich stars have other kind of molecular composition. Red giant branch have also other kind of composition. So I'm not sure this answers your question.
Yeah, it answered it. Complicated.
I think we have two other people have their hands up, and we also have a comment. So, Chris Kagi, you had your hand up first.
Yeah, thanks, Woody. Yeah, Dr. Rau, simple question, I hope. Your presentation did a great job explaining the method being used by Tess and Kepler to track the light curves of potential planets. But you were also saying that that to be verified, these have to be confirmed with another method. Could you describe briefly one or two of these other methods that are used other than observing the light curves to confirm the presence of the exoplanets?
So you want to tell me more about radial velocities?
If it can be done, within the span of time we have, I'd be curious to understand the method. I'm not familiar with that method.
Okay. Let me see. Maybe I have some additional slides here. I think so. Yeah. So actually, I have some additional slides where I can tell you more how this works. So let me share the screen again. Okay, can you see my screen?
Yes.
All right. Let me see. All right, so this is the radial velocity. I show you before that there are many techniques, actually 5 main techniques to find the planets. So radial velocity, transit, direct imaging, gravitational microlensing, and astrometry. They are more or less used, and you can see here how many planets have been discovered so far with each of these techniques. So for example, radial velocity, basically the gravity of the planets made the star wobbling a bit. And so as you can imagine, the bigger is the planet, the stronger is the effect that it has on the stars. And so small planets like the Earth make wobbling the star only a bit. But bigger planets like Jupiter, they have a bigger effort, and so the oscillation of a star can tell us if the star is a planet or not. How many there are. Okay. So the method utilized is called Doppler shifting. This method works as this should be an animation, yeah. So as this animation shows, basically. The planet causes an oscillation in the star in its orbit, while the planets basically move around, and so the waves can be different depending on this interaction and change their color. And so this method actually was one of the first one to find extrasolar planets, and it's one of the most productive, and it's mostly used to confirm planet candidates found with other methods.
Okay, so if I can, if I try to summarize to make sure I've understood correctly, with radial velocity, you're taking advantage of the fact that the center of gravity of the system is offset from the star somewhat, so that the star, as it orbits, wobbles, and then you are able to measure redshift, blue shift of the light of the star to see as it is coming and going. And I can imagine then, do you take advantage of the how much of the wobble there is, gives you a sense of the mass of the other body in orbit in the system, or other bodies in orbit in the system. Am I close?
Yeah, I mean, it's basically a gravity effect, and you use the Doppler shift to measure that. Yeah.
Wonderful. Thank you. I appreciate that.
Yeah, I mean, I can tell you more also about the other transit. We
oh, please.
We look at that one already. So I'm not sure if you want to know more about the transit, but here it shows you basically the light versus time. And you see the dip when the planet passes in front of the star. So in the case of single planet, we have of course only one dip. In the case of a double planet, we have 2 dips, and again the dips is correlated with the size of the planet. We have direct imaging that we hope to perform with, for example, the HWO. And then we have gravitational microlensing. So gravitational microlensing is among his numerous intuition. Einstein thought about the concept of gravity, as a mysterious attraction between objects, and so basically the objects deform the texture of the space-time, and so what we have with the gravitational microlensing is an object that is a lens, and that object that is the source. And you can see that basically the rate of light of the star that is more far away, they blend around the exoplanet. And around the star hosting the exoplanet. This is basically the same way that magnifying lens can focus the light of the sun only on one point on a piece of paper. The gravity of the planet and the star basically focus their rays of the star far away from the observer. And so you measure this curve that is called a Pachansky curve to detect where the exoplanet is. And then you have astrometry. So the Doppler variation are not the only way that the astronomers can find stars that oscillate due to the gravity of the planet. The oscillation can be also visible, like changes in the apparent position of the star in the sky. And this is one of the most rare one of the least common used way to find planets. So basically, you're revealing the position of the star that is moving in space. And it's really difficult to perform. The stars oscillate at a distance so small that it's very difficult to observe this and to observe with a very high precision the oscillation of planets, especially those small like our Earth. Yeah, so those are the main methods.
Okay, well,
Okay, thank you very much. I appreciate that.
thank you. Did anyone here in the room have any questions? Just to be sure. Okay, we have one more from Rob Parks. Are you still with us?
Yeah, if you can hear me.
Yep.
Thank you, Dr. Rao, for that presentation. I actually wanted to ask maybe one or two questions about AESI. I know it's probably still very much in the development stage, but I would imagine this is, I think in the video it mentioned that this was going to be something of a testbed instrument, because ultimately what I'm wondering about is limiting magnitude. Because at CHARO, we tried to do AGN science, and we can say that we got AGN photons on the camera, but that's about it. We never got fringes on it.
Yeah, so as you can imagine, taking fringes on the moon has a whole new level of difficulty. But so I don't know if it's you asking in the chat what's the resolution.
No, it's someone else.
I mean, it's this NIAC program. NIAC is NASA Innovative Advanced Concepts. It's for very visionary missions. So we are in the phase 1. There are 3 phases of this path. We are in phase 1, so it's the very initial study, and we just ended the phase 1 of our study. It confirmed the feasibility, but there are so many things to take care of. The dust issue on the moon, the power. How are we going to do that with the nuclear power or with solar? Of course, the need for astronauts. And so,
Imagine you also have a weight issue in terms of the size of the.
Well, actually, with Starship, I don't think that would be that would not be a limit. We'll that, if anything, that is the only thing that doesn't concern us because of the possibility of Starship, but of the cargo possibility of Starship. But yeah, there are a lot of issues that we will study more in detail in the next phases of EASY and to reply to the question in the chat, the angular resolution will be 100 times higher than the one of Hubble. So we are talking about milliarc seconds. And probably also microarc seconds. So it will start with 15 elements and a diameter of alpha kilometer.
And the individual, just sorry, Do you have an idea of what the approximate size of each element is going to be? Are we talking?
We are targeting 1 meter now, but we will need to place them on rovers. So that will depend also on the availability of, rovers, and there will probably have, an issue in terms of cargo of the rover itself that needs to move on the surface. And then, of course, there are also other possibilities like building tracks like VLTI, right? But we are still studying all these trades.
I look forward to seeing how it goes.
Me too, thank you.
We had two other folks that, Chris Orr, you had a kind of a question and a comment. Are you still with us? Do you want to ask your question, or? It looks like he was asking what degree of resolution you expect when observing exoplanets directly from future interplanetars like Artemis.
Yeah, I think Dr. Rau did answer that. And yeah, I think the follow-up, I was just kind of interested in, where that would take the field of study of exoplanets. Like, to what degree could we directly observe, cloud cover or large features, at least on exoplanets orbiting like the very closest star systems, like, Alpha Centauri and similar systems. Thank you.
So exoplanets observation with interferometry, even from the moon and even with such a high angular resolution, it's very difficult because of the brightness of the planet that is basically it's super dim. And so we are concentrating our science cases on other science cases. But we hope we will be able to, and still we are still studying many of these trades on how to optimize the instrument for various science cases. But we hope we'll be able to detect some lines, for example, Lyman alpha. It depends on the detector that we end up choosing. The detectors are changing like so fast. So probably between now and when this mission, if this mission goes ahead, and if this mission will be, will be truly placed on the moon, it will be so different than today, right? So science case will evolve also with time.
Okay. Well, that seems to be all of the questions. A couple of comments, but ma'am, thank you very much for your time. Thank you very much for the very interesting presentation. There's all sorts of interesting directions to go. We really appreciate your time and effort on doing this. And we hope you can visit with us sometime in person. So again, thank you very much. And I hope you have a good evening, and we really appreciate your time, and please come visit with us sometime.
Thank you. I would love to, and thank you for inviting.